Good morning, everyone. Okay. If you have any questions, please put them in the chat. Okay. I don't see any questions. So I'll start. So for the next few weeks, actually all the way to the end, we will be talking about linear transformations. Okay. So you have two vector spaces, V and W vector spaces with the same field. Okay, like reals or complex. So they both have the same field. F of V is equal to the F of W. Okay, all right. And hopefully you've seen this before in 223 and elsewhere. This is what we mean by linearity. You can split the sum and constants come outside. So that's why it's important to have the same field, because AV is in V and ATV is in W. So you need this A to be in the same field for both. Okay. This domain, so I have a picture here. Okay, I'll just, yeah, so you have, this is V, this is W, and you have an image inside W. This is image of T, and this is called the domain. This is called the target or codomain, and this is called the image. So W is not the image, it's the codomain. That's what they call it. Okay. All right. Now, suppose your spaces are finite dimensional, V and W, and right, so we have finite dimensional vector spaces, and we evaluate T at each of the vectors in terms of W. So we get some coefficients, right? Because this guy is in W, so it can be written as a linear combination of W1 to Wn, and we do it for each J. Then the matrix representation is simply the array of coefficients. So this guy over here are the coefficients for TV1. And this guy is for TVN and so on, TVJ. Okay, so that's what we call matrix representation, and we write it in this form to mean basis V in base W. So this is the V basis and this is the W. Usually we write it calligraphic. So this is the W. Okay. All right. So let's do, but yeah, we'll come back to this next week. So we won't do much of this week, but we'll come back to it. All right, so let's do an example, the simplest one of all. You have Rn, and you simply map a vector x to itself. Okay, that's the easiest possible. And let's try to show linearity. So linearity follows because identity on combination gives you the combination, and then you just do it in reverse for each element. Okay, easy enough. Right. And then how do you find the matrix representation? Like we said, for each k 1 to n, you express the output. This is the output in terms of the vectors in the image. This is W. And I mean, this is the easiest case possible, right? So EK is only equal to 1 EK because because this is the standard basis. So EK is 0, 1, 1 in the kth position. And they're Li. So they don't have any dependence, which means that the only non-zero coefficient will be the one of the vector itself. Okay, so that's what happened here. And that means that the coefficient for ID 1 is this guy, and coefficient of ID En is this one. So this is the matrix representation of EE. Now, let's see. Let me ask you a question. So let's take Rn with even simpler R2 with the standard basis, call this V, and then take W R2, but with, let's see, 1, 0, 1, 1. And now the question is, call this basis, I don't know, beta, call this basis alpha. Can someone tell me what's the identity matrix representation going from alpha to beta? Does anybody know? What would be the column vectors for this matrix? Mm-hmm. Right, so exactly. So ID of yeah, I know. So ID of 1, 0, and call this beta 1, beta 2. What is it? It's 1 beta. So identity on 1, 0 is 1, 0, which is 1 times beta 1 plus 0 beta 2. And and then identity on 1, 1, this is 1, 1. Sorry, identity on 0, 1. This is 0, 1. And now you have to write it like that. So let's see. So I need 1, 1. And you need to put a minus over here. And this is 0, 1. Okay, so let me see. So what do I want? I want to kill. So I want to keep this. And I have 1, 0, right? So I need to put a minus sign over here. So it's like this. So this is minus plus. Okay, so the first guy will be 1, 0. And the second guy is 1 and then minus 1. So you have minus 1 and 1. Okay, so this is the identity matrix of alpha beta. Now, if you wanted to do identity matrix on beta alpha, then you will get what you guys said. So it will be 1, 0, right? This is the beta 1. This is 1 times 1, 0 plus 0, 0, 1. And then identity on 1, 1. This is 1, 1, which is equal to 1, 0 plus 0, 1. So you get 1, 0, 1, 1. Okay. So it's a little bit tricky. So when you go this way, the matrix representation is the one over here. But when you go that way, the matrix representation is over here. Is that okay? Lindsay, yeah, go ahead.
Yeah, so the 1, 0 vector that you first wrote, like next to IDB, that's a vector coming from the alpha basis,
Right. So
and so then what we're trying to do is find a combination of betas that gives us that alpha. Is that it? And then
exactly.
using those two, then we construct the identity matrix. Is that the idea?
Yes. Yep. Yeah. Okay. Yeah. Exactly. Yeah. Absolutely. So we when your domain when in your domain you have basis alpha, you have to evaluate at these vectors, so alpha 1, alpha 2, and in terms of the image vectors, beta 1, beta 2. But when you go the other way from W to V, then you get the matrix that people talked about. Namely, you evaluate at the beta vectors in terms of the alpha vectors. So there was a minus sign here. All right. So yeah, it's a little bit tricky.
Oh, sorry, I have another question. So what you did on the right there, where you wrote IDB, was that is that B supposed to be an A then?
Sorry, what?
Where it says like IDB is equal to 1, 0.
IDB is equal to 1, 0.
And then it says equal to 1 times B plus 1 times B1 plus 0 times B2.
Yep.
Yeah, like in the where you wrote IDB, like is that not a B? Is that 1, 0?
You're talking about the one I'm circling?
Yeah,
Yeah,
that.
so this is okay because we're evaluating at the basis vector 1, 0,
Mhm.
which gives you 1, 0, and then it would,
Okay, I see.
yeah, okay.
Okay, thank you.
Yeah. Right, so you get the identity matrix for this, but generally it's harder. But there are many maps out there, and you have this map over here. Any guesses why this is not linear? Um, uh, which property do you think fails? Do you have, yeah. Mayma says, when we multiply the first matrix, will we use the alpha or beta basis? I'm not sure what you mean by multiply. Multiply what? I don't know what you mean, like multiply with the vector? So let's see. So this, yeah, so I guess I should go on the right. So the first guy, the ID alpha beta, takes in elements from V. So it takes some guy from V and maps it into some guy in W. And then the other one, the ID beta alpha, takes some guy from W and maps it to some guy in V. Yeah, these are that's right. They are change of basis. That's right. But we'll come back to this. I just wanted to, prepare you in a way. But when we use 0, 1, we can get 1, 1. We can't get 1, 1. Why should we get 1, 1? It doesn't map vector to vector. It maps a vector to a linear combination. So, right? So 0, 1 gets mapped to 2 elements. This guy plus this guy. I keep forgetting, but IDB alpha is from A to B. So yeah, so the way I think about it is it evaluates up here in alpha in terms of the beta. There are some other notations I've seen. Some people write alpha to beta, whatever helps. But in the book, that's the one he uses. Okay, so well, let's just follow the book. The book goes by, I like that notation too. I've seen it elsewhere, but let's just stick with the book so that we have consistency. So in the book, he writes alpha beta. If you want to put an arrow in between, that it's fine. I mean, I don't think they will they will kill you for it. But I like this one more, of course. But in the book, they go with this. Yeah. There's no arrow in between, but I wrote the arrow. You can write it. I don't think anybody will complain. No, nobody will complain. If they complain, come to me. Anyhow. So yeah, this map is not linear. And the reason is you do not have scalar multiplication. So t at 2, 2 is equal to 2 times 2. But t at 1, 1 is 1 times 1, which times 2 is 2. So so you do not have that a of 1, 1 is not equal to 2, 2. So I might as well write 2 here. So 2 times 1, 1 is not equal. What am I writing here? So let me write it like this. So 2 times 1, 1 is equal to 2, 2, which is not equal to 2 times 1, 1. So these two are not equal, but they should have been. So you do not have linearity with a scalar. Namely, you do not have ATV. TAV is not equal to ATV, which is what you want. Okay, moving on. So you do not have linearity. Yeah, coming back to this matrix stuff. So again, we'll come back to this next week, but I just want to prep you. So given some map T and two spaces V and W, you have that T is uniquely determined on the basis vectors. So in other words, you can construct maps, linear maps, by evaluating at basis, by giving array of values. So all this proves that is that T is uniquely determined by its matrix representation. Okay, uniquely determined by its matrix. Okay. So it means, because it's not obvious a priori, right? So what we're saying here is, if you give me a matrix, I can give you the map. And if you give me the map, I can give you the matrix. This one is obvious, namely to give you the matrix, but the converse is not obvious because the bases can be different, all kinds of things. So that's what we're proving here, unique correspondence. Okay. So how do you do these proofs? By contradiction. You assume, okay, contradiction. I mean, you assume that there are two maps that a priori might be different, and you have them equal at the basis vectors. So namely, you have that S of alpha beta is equal to T of alpha beta. Okay. And we want to show that in fact, T and S and T are equal at every single vector, not just the V guys, which are just n values, right? It's like, you know, you have Rn and you show that two maps are equal only at the EK. That's the power of it. You don't have to check that they're equal everywhere. You can just check at the standard basis. So that's another way to use this result. There's many ways to use this. All right. So what do? Well, the logical thing, you want to show equality at X. So let's come back to our bases, V1 to Vn, and you have this linear combination. So yeah, T of X is equal to T of the linear combination. Then by linearity, you can bring out the sum and the scalars. But then here we use the assumption, right? That they equal, that they have the same matrix. So S alpha beta is equal to T alpha beta. And then you undo linearity. Okay, so indeed, they're equal. Okay. Oh, and this is only for linear. Yeah. So, oh, that's a good question. Let me find an example. So I want, let's say in R2, take 1, 0, 0, 1, and now I need two guys that are equal only there, but they're different. T of X. Yeah, can someone think of two maps such that T of EK is equal S of EK, but these guys are not equal? Let me throw it to you if you have some idea, anybody? Okay. Yeah, if you have an idea, let me know. I think I have to use some sort of exponential or something. I have to think about this. Let me see. How about you take T to be XY and then, oh yeah, okay, yeah. So take, yeah, same field. So here's the example. Take T to be XY and take S to be the zero map. That works. So, okay, identically zero. All right. Okay. All right. So that was the trick. And let me justify in more detail how we did the linearity step. So it's not obvious a priori because you have n terms. So how do you do it? So you have A1V1, and then you have the rest of the terms, J2 to N, AJVJ. And then you call this guy U, and you call this guy, I call it W. So then this guy is TU plus V, and then you do the linearity. I mean W. And you keep doing this. So that's how we get the, so you do it for the next guy. Okay, so you have T AJVJ, and then you can pull out the constant. All right, so we bootstrap. Yeah, they have to be in the same field. For these transformations, we always take them same field. We mentioned it in the beginning. Otherwise, we can't define a linearity for these maps. All right, so I do another example. So what do I do? So I just do more examples, and then it's a lot of examples. Anyways, let's do some examples. All right, so let's make sense of the above result. The above result says you give me a space and some bases. So this is a basis for R2, 1, 1, and 1 minus 1. And you just, and then you say, suppose the T is a linear map that that does this. Okay, so it sends these two vectors to these two, and that uniquely determines T. So there is no other linear map uniquely determines T. So yeah, let me test you a little bit. So T of, call this alpha, and take beta to be the standard basis for R3. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. Any ideas? What's the what the matrix will be? So any ideas what call these guys here U1 and U2, these two vectors. So any idea what should I put in the columns of this matrix? Anybody else? Do you all agree with this? Disagree? Okay, yeah, so exactly. It will just be U1, U2. And the reason is T11 is equal to 2 times E1, 0 times E2, and -1 E3. And same thing for the other one. So 2, 0, -1, 0, 0, 1. All right. And then we have to identify this guy, this linear map. So yeah, so we know how it acts at individual elements. We want to see how it acts on everything. So you gave me some V, and this is in the standard basis. So imagine V is like, I don't know, 4, 5, something like that. 5, this is 5, 4. Okay, this is V, and this is written in the standard basis. But here we want to write it in the in this new basis 1, 1 and 1 minus 1. So pictorially it looks like the same vector, but then you have to use different bases. So this is 1, 1, and 1 minus 1 is over here. So this is 1 minus 1, and this is 1, 1. And your vector is over here, 5, 4. And then these are your new axes. So this is one coordinate, and this is the other coordinate. So call this alpha 1, alpha 2. So V in the new basis alpha will be A1, A2. I shouldn't use, I should call this something else. Let me call it like R2, R1. Okay, so we take this to be alpha 1 guy, alpha 2, and when even pictorially you can see that it won't be 5, 4 because you moved the bases around, but it will be these numbers that I will now compute. So you give me some general AB, and I can write it in terms of 1, 1 and 1 minus 1 with these coefficients. So you can check this. We have A plus B2 plus A minus B2 and A plus B2, and then minus A minus B2. And this will give you A over B. Okay.
If
Yes.
you have time, can you quickly like go through the process of finding those coefficients?
Yeah, sure. So let's see. How would you do it? What did I do? Oh yeah. So you so right. Let's go here. So V is equal to AB, and then this is A10 and B01, and then you express the 10 in terms of the so you write 10 in terms of, I don't know, let me call it C1 11 and C2 1 minus 1. So let me just do this one, and the other one is the same. So you want to get 10. So you keep the first one. Oops. So you want to keep this, and you do want to keep that. So you put a half for both. So if you put a half for both, you will end up getting 10. Is that okay? So then you just plug that in over here. So you will have A half 1, 1, A half 1 minus 1, and you will do the same for the 0, 1 vector. And when you do that, you will get the one I mentioned. Is that okay? Hello?
Yeah, yeah,
Okay.
thank you.
Right, so you get this. Right, but we still have to find the map. So now, now that you did this, now that you brought it in the basis where the map is evaluated on, you use linearity. So you just use linearity on the first step. And now here, you know exactly what T is. It's by definition. By definition, T of 1, 1 is 2, 0, minus 1. And T at 1 minus 1, it's 0, 0, 1. And then I just add them in vector addition component wise. So that means that T of AB gets mapped to A plus B, 0 minus B. So that's it for that. All right. Another example done in your book is called the projection. So let's spend some time on this because we'll come back to it in 2 weeks from now. So with inner product, all that stuff. So what is this map? So you again you can take any vector space, but I just take R2 here, and it has to be the same vector space. So you have to work in the same vector space, and you have to project. So here I did the simplest kind of projection, namely I take the 0, 1 and I squash it down to 0, and I preserve elements along the axis. So that means if you give me any other element, I throw it down to its first component. So if this is AB, I send it down to A0. So this is called projection onto the first component. Okay, so let's find the map. Let's find that indeed it's A0. So you take a general AB. So this is much easier. You split it. So AB is equal to A10 and B01. And you use linearity over here. But now you know what the map does at this basis. You know that the first one gets mapped to itself, and the other one gets mapped to 0. So this is the 0 vector. Right. So the general effect is that T of AB is equal to A0. So you forget the second component. That's called a projection. All right. But this has a general formula. It's the following. So let me write it in bigger. So if you want to project at a vector U, some vector AB, let's say U is U1, U2, then this is the following. So you will have U1 squared, U2 squared, and then A U1, B U2, and then times the vector U1, U2. So this is the general formula of the following effect, namely, you give me some vector U that has some span. So this is U. And then you give me some general vector AB. Then this projection does the following pictorially. You send it over here. So this vector is called the projection of AB to U. Okay. So this is what projection does onto an arbitrary vector. I did the simplest case of projecting to the real axis, the x-axis, But more generally, you can have what I wrote here, where you project onto any vector u that you like. Okay, it projects at a right angle, right? No, this is not right angle. Oh, you're talking about this. Yeah, this is a, well, I mean, right angle. This works in any dimension. So you could have, you could have a vector like this, and how do you say it? Yeah. No, it's always, yeah, you can define an angle. You're right. Yes, it's always like a right angle. That's right. It's just in higher dimensions, it's not always clear what we mean by angle. But of course, yeah, it's always right angle. Yes, yep, absolutely. So what's an interesting fact about this that we will come back to is the following. So let me briefly talk about composition, and we'll come back to it on Friday. So composition of two maps. T going from V to W and S going from W to U is denoted as ST, and it acts as follows. So ST of V is simply S of T of V. All right. Okay, so it does something like this, right? You have some effect like this. This is T, and this is W. So this is S. So it takes some vector like this, V, maps it to some vector TV, which maps it to some vector STV. All right. Now the amazing thing about projections, which we'll come back to many times, projections have the following property, namely this projection we just did. So let me write like this: projection at U of projection of U of V is equal to projection of U at V. Okay, so in short, we write this as P squared is P. So and pictorially, it's obvious. What it says is, so you have some vector U and you have a vector V, and you send it down to this vector UV. But then if you do this again, so call this guy, I don't know, W, PUV of W is W, because this guy is already in the span of U. So there's nothing else to project to. It's already projected. Anyway, so this is a fact. We'll come back to it many, many times. So I wanted to do it here. Okay. All right. So projections send themselves to themselves. All right. And yeah, let's do our example for this. So projecting to 1, 0 means you do the following operation called dot product. So let me talk about this as well again. So the dot product of two vectors VU is equal to the summation of each component. So V1, U1, yeah, let me remove this V1, U1, all the way to Vn, Un. And so let me ask you a question. Let me see if you know. So if VU is 0, what can you say about them pictorially? Does anybody know or remember?
The vectors are at 90 degrees, like perpendicular.
Perfect. And then what if VU is -1? It's a little bit. I'm just curious if people know. Yes, exactly. So in general, you have the following formula. VU is equal to normal V, normal VU, cosine theta, where theta is their angle. So, so yeah, theta will be pi/2 because theta of cosine of pi/2 is 0. Cosine of pi is -1, 180, and so on. Okay, so the dot product has this very interesting formula, geometric formula, in 2 dimensions. So this is only true in R2. It's not true in general. But UV will have to be 1. Yeah, it will be 1. Yep. So it will be like, what's an example? I don't know, it could be all kinds of examples, but yeah, you need their norm to be 1. So just to be clear, U of this is the following. It's U1 squared plus U2 squared. And V is same thing. So both of these, in this example, will need to be 1. Yeah. So I'm not sure what values you can take. They just have to be on the unit sphere. So there will be some antipodal vectors, UV. This is radius 1. Okay, good. All right. So we'll come back to this, but start reading on projections and just to prep yourself from your whatever you saw it. So I know in 2 to 3 people saw it. So yeah, if you can start reading a little bit on it, because we'll come back to it many times. All right. Yeah, some other examples. Let's go through them. So all kinds of transformations in space are linear. So shear transformation, the picture was something like this. You take this and you shear it. So this is the shearing. And one example is this matrix over here. So it takes a vector like this and it moves it to some direction. So here, for example, you take X and you move its second component by X. So this is X. This is X2. Yeah. So this is X1, X2. All right. So yeah, and yeah, you have reflections. So you take some vector here and you map it here, and also rotations. So you take a guy from here and you move it, let's say by theta. All these guys are linear because they can be represented by matrices. Okay. Yeah, I gave you some more examples. So let me talk about the one I'm gonna come back to very quickly. So from calculus, we also have that the integral and derivative operator are linear. So we will also use that a lot. So this is called the sum rule. So f plus G prime is equal to CF prime plus G prime. So we will use this next time on Friday. So see you. Have a nice day. Yes. Sorry again, what is C01? Yeah, C01 is continuous functions on 0, 1. So pictorially, you go from 0, 1, and you have all kinds of stuff like this. So these are the 0, 1 functions. So you take any continuous function and you restrict it to 0, 1. Any questions? Yep. You're welcome. Okay, so if there's no question, I don't see anything. Okay, all right. See you on Friday.